Good afternoon, everyone. Davut Gehadari.
Yes, sir. My name is Davut Ertekin. In fact,
Okay.
I'm I have two nationality, Iranian and Turkish. So I'm here with my Turkish citizenship name, Davut Ertekin.
Okay. Thank you very much, Mr.
Thank you.
Davut. Your paper ID is not, I think,
It's 30,
30.
38. The
Okay.
paper is 38. Yes, the first one.
Okay, we can change 38, please. Bursa Emo.
Yes. From Bursa Technical University and Valeo Automotive Industry Fabrication.
Okay, Professor. I think your paper is first.
Yes.
Okay. Sinan Baydan.
Hello.
Hello, Sinan Baydan. Your paper ID is 7, and I think the last paper yours.
Yes.
Okay.
Yes.
Okay, thank you, Mr. Sinan. Yunus Emre Yagan. Could you open your camera? Okay. Okay. Good afternoon. Welcome, Mr. Yunus. Your ID is 29. Or which one, third or two? Second? Could you open your microphone?
Yes.
Which one? Second or third paper?
Second.
Okay, thank you. Thank you. We more one presenter we need. I think third paper. We are waiting for him. Let's wait a bit more, please. Okay. Welcome,
Hello.
Mr. Ibrahim. Hello.
Hello, this is Ibrahim speaking here.
Okay. Could you open your camera,
Yes, of course.
please? Okay. Thank you very much.
Yeah.
Okay. Okay. We can start the session. First of all, good afternoon, everyone. Welcome to session 25, Power Electronics-1 of the 13th ELECO conference. First of all, I would like to thank the participants and audience on behalf of the conference chairman, Professor Kalanderli, organizing and executive committees. I will chair this session. My name is Murat Yilmaz from Istanbul Technical University, Electrical Engineering Department. In this session, there are 4 papers and we will have 4 speakers. Each speaker will have about 20 minutes for presentation and 5 minutes more for question and answers. Dear audience, if you have any questions about the presentations, please write and send your questions from the chat section of the Zoom, or you can raise your hand. Okay, let's start the session. Our first speaker from Bursa Technical University, Professor Davut Ertekin. The title of the paper is An Efficient Full Wave and Switched-capacitor-based AC-DC-DC converter configuration. The authors of the paper, Davut Ertekin, Mesut Berke Bilgiç, and Bulent Mutlu. Okay, Professor Ertekin, if you are ready, could you please first introduce yourself briefly and then please start your presentation. Thank you, Professor.
Thank you. It's my pleasure to present my paper, my joint paper with Valeo Automotive Industry with you, dear my colleagues. Can you see my
Yes,
screen?
Professor.
Okay.
Yes, Professor.
Very well.
Please shift the presentation mode.
Mm-hmm.
Okay, thank you.
Okay. I thank you again. Dear colleagues, my name is Davut Ertekin. I'm an assistant professor in Bursa Technical University, Department of Electrical and Electronics Engineering. In fact, this paper is a joint study, and I'm working as the supervisor professor from Bursa Technical University with Valeo Automotive Industry and Trade Cooperation from the Bursa. We did this project and it is R&D project, and a section of this project now here will be presented entitled Analog Controlled AC-DC Converter Design for Alternator Tests. My other co-workers from Valeo Automotive Industry are Mesut, Berke, and Bulent, Matlab. The paper entitled is an efficient full wave and switched capacitor-based AC-DC converter configuration applicable for high voltage gain industrial utilization. In fact, what was the main basis of this study? If I want to explain for you, the basis of the study is established for the applications that needs for unexpected and formal voltages in industry. For example, as you know, we have some of the industry voltages like 48, 24, 15 or 5 volts as the DC voltages, but sometimes we need to other level of the voltages. For example, in this factory, we need to three different levels of the voltages that are abnormal normally. For example, 8 volts, 13.5 volts, or 18 volts that are not very common voltages in industry. So for this study, we at the first stage, by using the grid voltages as the 220 volts as the RMS voltage, we are converting this AC voltage to a DC voltage. And at the second stage, we can convert by a DC buck or boost converter to the desired level of the DC voltages. In this study, we are presenting a high gain DC converter. So we are talking about the boost converters, and we are converting the 24 DC voltage to the 200 DC voltage at a 0.5 of the duty cycles. In general, if I want to talk with you about the features of a good and proper DC to AC converter, I should say that we need to robust and resist in maintaining the output characteristics of the converter. As you know, in a converter, normally the load is changing, and we have not the fixed loads at the output ends of the converter. Also, sometimes we have not fixed voltages at the input side of the converter. It means you can have 220 voltage, or sometimes 240 voltage, or 180 voltage that is alternating and changing. So we have to present a fixed voltage for the load at the end nodes of the converter. So this converter, the person, the converter, will do this duty in a good management. For the next stage, I want to say you about the proposed structure. As you can see here, for the first stage, by considering an 220 volt as the AC and grid voltage, the 50 hertz, we are going to fix this voltage to a 200 voltage as the DC voltage for the loads and with low THD values. So As you know, for a good power converter circuit, we don't have the THT problem in the inside of the converter. Here you have an AC voltages at the input side, but if you use from a half-wave controller, half-wave rectifier circuit, you will have a power factor problems, as you know, and it's because your current average value of the input current is not zero, but voltage is zero, so you have a huge amount of the power factor, and so you have to compensate this value, but an extra circuit. So normally for this stage, and full wave rectifier is preferred, as I showed for you. In fact, the novelty of our study is related with the figure 2, and the figure 1 is conventional circuit. But here I will present you the calculation for find the filter side for the figure 1. It means I'm investigating the amount of the inductor and capacitor here for you, and the work condition of the rectifier. In figure 1, as you can see, we have totally 4 power switches. 2 switches S1 and S2 are work simultaneously, and the switches S3 and S4 also are work simultaneously, but in time interval that are the other pair is not activated. It means S1 and S2 is activated when S3 and S4 are deactivated, and vice versa. And the next step, the filter here, the LC filter, LF and CF are trying to present a pure DC voltage here. Since this study are investigating different level of voltages, so I decided to convert this AC voltage to a DC, but in a very low step. And then if we need to other high voltages, we can use the figure 2 structure to enhance voltage from, for example, 24 volt to 200 voltages. As you can see, and as you know, for a full wave rectifier configuration, at the output ends of the switches S1, S2, S3, and S4, we have a voltage, average voltage equal to 2 Vm over pi cosinus phi and cosinus alpha. Alpha is the firing angle of the switches. So if we have to have a voltage equal to 24 volt as the DC voltage, input this DC converter by 220 volt as the RMS voltage of input side, and 3.14 for the pi, we can easily find the angle. This angle, or alpha, is the firing angle of the converter. It means if you switch these power switches or driving switches with different level of the power angles, you can have different level of the DC voltages at the input side of LC filter. So for implementation or simulation stage, as you know, we cannot give this angle directly in, for example, in Matlab Simulink. So we have to convert to the times. So equations 4 and 5 are presenting to drive the S1 to S4 switches by considering the 50 Hertz as the input frequency. So as you know, at this stage, we have to find the value of the capacitor and inductor in the filter. So as you know, the average voltage across an inductor in a time period is equal to 0. So the voltage at the input side of SC filter with a very good approximation is equal with the voltage across the capacitor. So in fact, this capacitor is fixing the voltage, but we need also to a fixed current. So inductor here acts as a smoother and smooths the current for the next configuration for the figure 2. So as you know, and from the power electronic fundamentals, when you have not a sinusoidal voltage or current, you can estimate this by Fourier series and present the equivalent circuits, equivalent equations through the Fourier series. So the amplitude of the inductor current for N2 as the first AC term for the current can be present with equation 7. So the value of the inductor easily can be found through the equation 9. There is a problem here. I should present with equation 8. Here, as you know, the average voltage should be very greater than the inductor current for the second harmonic or AC term. So we can present the equation 9 here, or equation 8, in fact. So easily we can find the amount of L. In this equation, Rin is the input impedance of the DC-DC converter, as you can see here. In fact, the CF is here, we have not V-in for the figure 2, and V-in, in fact, is the output ends of the capacitor CF. Here now we have 24 volt as the DC voltage. So we are going to talking about the figure 2. As you can see here, I have a quadratic boost converter structure before the power switch M, and after that a normal switch capacitor structure by applying Q power diodes D4 and D5 and capacitors C2 and C3 are added to the conventional quadratic boost converter that can easily act as an voltage doubler and increase the voltage across the power switch M to 2 times. It means if you have voltage equal to 100 volt across the power switch, you will have a voltage near to 200 voltage across the load. But how we will do by this equation? As you can know, for a DC-DC converter, when the power switch is activated and deactivated in 2 different time intervals, so we have to present the circuit for both of these modes. It means for figure 3, we have the switch is in activation mode, and for figure 4, we have the switch with deactivation mode. For the figure 3, as you can see, inductors L1 and L2 are charging because the power switch M is short circuit. So diode 1 is in on mode, and D2, because the anode has the voltage near to 0, cannot be conducted. So both of the inductors L1 and L2 are simultaneously charging through the short circuit power switch. For the switch capacitor side, as you can see, capacitor C3 are charging through the power diode D5, and this makes to C2, capacitor C2 to be discharged. It means the C2 and C3 are working oppositely. For the figure 4, as you can see, when this power switch is deactivated, power diode D1 is deactivated, but D2 will be activated because the cathode of the D2 now has a voltage across the C1 that is discharged in the previous state. For the second side of the converter, and after the power switch, as you can see, now C2, capacitor C2 is charging through the diode D4, and the C3 also is discharging in small. It means C2 and C3, as you can see, are charging and discharging oppositely from both the figures. Here I present some of the equation to find the gain of converter. For that, I used voltage, drop voltage equal to VD, as you can see here. VD, in fact, the voltage drop across a power diode or inductor. When we have two states for the time intervals that the switch is in on and off, so we have two duty cycles, D and 1 minus D. D present the time interval that the switch is activated, and 1 minus D is presented the time interval the switch is deactivated. So easily we can find the voltage across the capacitor 1. Capacitor 1, where was the capacitor 1? As you can see here, for the capacitor of the quadratic boost converter C1. So after that, we are going to find the capacitor voltage across the capacitor CO, or output capacitor. As you can see, VO1 is the voltage across the power switch, and after that, since this switch capacitor structure is a voltage doubler, you can have 2 times greater of the voltage across the power switch. So easily you can find the equation 40. For obtaining this equation from the equation 12, we can erase the second phrase of this equation, because VD really is very small in front of V in over 1 minus D with power of 2. So with very good approximation, we can find the equation 14. As you can see, the gain of the converter.
Professor Ertekin, you have 5 more minutes, please.
Okay, it's enough for me. As you can see here, with duty cycles near to 105, we can have a voltage at output size 8 times greater than the input voltage. It means for a thing about 25 or 24 volt as the input voltage, we have 200 voltage, DC voltage at the output side. Here you can find my simulation result. As you can see, firstly for the AC to DC converter, as you can see, we have an AC voltage and AC current for the inside of the converter. And as we expected for the output side, we have a 24 volt, near to 24 volt with a thing about 2 ampere as the output side. Upper type near to 15 watts as the as our prototype is near to 15 till 80 watts. And here we can find the voltage of the input and output side of the converter, DC-DC converter in figure 1 and figure B. As you can see, it's easily converted the 24 voltage to the to 200 voltages. And from the figure 6C, you can see the voltage across the switch is near to 100 volt, and that is easily can confirm our theoretical equations. Also, you can see here the current of the switch that after it spikes in the at the start time, it remains near to a thing about 2 till 3 amperes. Also here you can see the current equations for current waves for the inductors L1 and L2. As you can see, the current level is very, very good and near to 0 till 5 amperes. And at the end, for the end figure, I present the gain comparison with some of conventional converters you can see here, and it shows that our proposed converter can easily, by applying some very different, very cheap components, can increase the voltage gain. As you can see, for example, here and after a duty cycle equal to 0.5, our converters have gains, they have a very good gains in comparison with other converters, and you can see here. So as the conclusion in this converter, and as in this paper, we presented 2 different structures. Firstly, for AC to DC converter, and then for this DC converter, it means this converter can be separately applicable for AC-DC applications or DC to DC applications. And also, as you can see, we use a full wave AC-DC converter that can reduce the power factor problem in the power converter structures. And also, as you can see, we have only one power switch in the DC converter that can easily decrease the complexity for the control topologies. And also other thing that I can see, yes, an accurate and unchangeable voltage across the main power switch can be followed by the equation. As I said, this was a joint study and R&D project, a part of R&D project between me from Bursa Technical University and Vale Automotive Industry and Trade Company in Bursa. If you have any question, I will be glad to listen and respond to you.
Okay, thank you, Professor Artekin, very much your nice presentation and contribution.
Thank you.
Now we can answer questions from our audience. I don't see any question in QA section. Is there any questions from speakers? No. Okay. Okay, I have two short and quick questions. Could you go to slide 8 and 9, please?
8 and 9, please. Okay.
8 or 9. Maybe 9 is enough.
Here.
This is 9? No. Next one, please.
The second one. Okay.
Next one. Okay. If you look at the figure 6b, could you comment on the settling or response time of the voltage to the desired reference?
Yeah. I should say that, dear professor, this converter is not designed to work for seconds or I don't know, for the minutes. This converter is designed to work for days, for weeks. For example, you have a PV panel, for example, and you are enhancing this voltage to convert to a grid voltage, okay? So here the voltage times, for example, equal to 2 milliseconds or 5 milliseconds is not important at all. In fact, the reason that I showed the figure by these features that show that the voltage amplitude is very near to 200 voltage. Also, this voltage, as you can see, the settling time is a thing about 0.03 millisecond. It means a thing about 30 microseconds. That's really a very good level of the settling time.
Okay, thank you, Professor. The second question is, could you go to next slide, I think 10.
Certainly, yes.
Okay, in figure, you give the voltage gain comparison for various high gain DC-DC converters.
Yes.
Could you make a comparison in terms of efficiency, power density, or
yes.
cost, etc.?
Yes, you are right. In fact, normally for our journal papers, I do many of these parameters. And if you see my papers, we have a very different configuration, especially for inverters and DC-DC converters that I present all of this. But for the conference paper, I don't know, maybe it was a good idea to add at least one of them or some of them. But in this paper, only we presented the gain conversion. But you are right, the cost conversion, also the voltage stresses, current stresses across the main power switches or power diodes can be issue and can be added.
Okay, thank you. We would like to thank Professor Artekin for participation and contribution to the conference. Thank you very much.
Thank you because of your amazing conference, and from 2018, I have papers in this conference and participate in this conference. It's my pleasure.
Okay, thank you.
Thank you
we move on the second presentation. The second presentation from Kutahya Dumlupinar University, Yunus, Emre, Yagan. The title of the paper is Prototype Development and Verification for Grid-Connected Three-Phase, Three-Level NPC PV Inverter. The authors of the paper, Yunus, Emre, Yagan, and Kadir, Vardar. Mr. Yagan, if you are ready, could you please first introduce yourself briefly, and then please start your presentation and share presentation, please.
Yes. Thank you. Hello, everyone. My name is Yunus Emre.
Sorry, Mr. Yagan, could you shift the presentation mode, please? Thank you.
Presentation mode. It's presentation mode.
It's not presentation mode. I don't remember short, but on the right icon.
Yes, I click it. But I don't know why it isn't.
Okay, you can go ahead, please.
Thank you. Hello, everyone. My name is Yunus Emre. I'm a research assistant at the Kutahya Dumlupinar University, Turkey. Today, I am going to talk about prototype development and verification for grid-connected three-phase, three-level, neutral point clamped photovoltaic inverter. My presentation is divided into 6 sections. Firstly, I will make a brief introduction. Then, I will talk about three-phase grid-connected NPC PV inverter system and its control block diagram. Then I will present Matlab simulations of the inverter system. Then I will present cooperation simulations of the Matlab with microcontroller of the inverter system. After that, I will present results and comparisons of the simulations. Finally, I will conclude my presentation. In power electronics applications, it is a useful method to simulate the circuit with a simulation program before the circuit is built in the laboratory environment.
Sorry, Mr. Yunus, we don't see your slides. Please check it.
I share again.
Okay, we can see.
In power electronics applications, it is a useful method to simulate the circuit with a simulation program. Before the circuit is built in the laboratory environment. Thanks to this simulation environment, the behavior of the whole system can be analyzed beforehand, and the effects of each parameter can be observed separately. In the light of the results obtained from the simulations, a laboratory prototype is designed. In experimental studies, in addition to power stage, microcontrollers are used to perform mandatory tasks, such as reading sensor measurements, calculating control algorithms, and switching semiconductors at high frequencies. After the simulation for the system is completed, it is necessary to be sure that the controller card is programmed correctly before proceeding to the laboratory prototype. Otherwise, serious damages may be caused to the power circuits of the system. Therefore, in this study, firstly, a three-phase grid-connected photovoltaic inverter system is modeled by using Matlab Simulink. Then, a prototype inverter control card design is designed by using STM32F407 discovery board. Then, a communication system is established between Matlab and microcontroller. Because of this communication system, before real power circuit implementation stage, prepared control algorithm software is tested and possible software errors can be prevented. Grid-connected PV inverter circuit is shown in the figure 1. With such a system, DC energy coming from the sun is transferred to utility grid by inverting AC energy. In the literature, there are many PV inverter structures with different features such as single-phase, three-phase, single-stage, multi-stage, multi-level, two-level, with transformer and without transformer. In this study, three-level, single-stage, transformerless, three-phase structure is preferred. The reason behind choosing the transformerless and single-stage structure is to reduce the cost and size of the inverter system and increase efficiency. The control system block diagram designed for system is shown in figure 2. This control system consists of 6 main steps. And maximum power point tracking control, DC bus voltage control, capacitor voltage balancing, grid synchronization, current control, and pulse width modulation. In this slide, Matlab simulation model of PV inverter system is given. This is PV source. This source is a PV string and consists of 23 solar panels. These are power circuits. This is three-phase utility grid. Their values are given in the table 1. This is controller. These are controller subsystems. Simulation and controller sampling times are also given in the table 1. This control system is the same as the control system in the previous slide. Simulation results will be presented comparatively with the cooperation simulation results. In this section, a cooperation of microcontroller with Matlab is carried out to test the prepared software safely before hardware implementation stage. Cooperation simulation structure is given in the figure 4. It can be seen from the figure that the inverter control blocks were removed, and in order to prepare a communication between Matlab and microcontroller, an S function block was added instead. With this S function block, data exchange between Matlab and microcontroller is performed by using UART protocol. A UART protocol used in the study with 1 stop bit, no parity bit, 8-bit data, and 115,200 bit per second. Furthermore, signal conditioner and ADC sampling blocks, these are for simulating sensor gains, signal conditioner circuits, and analog digital converter sampling rates, so that the data from the simulation is the same as the data from the real power circuit. In figure 5, the photograph of the physical environment is given. Personal computer, microcontroller, and USB to TTL converter. USB RS 232 converter. The connection between the personal computer and the microcontroller is provided this converter. STM discovery board is preferred as microcontroller because it not only has enough capability but also it is not expensive. Micro C Pro for ARM compiler is used for programming microcontroller. Figure 6 shows the flow chart of the cooperation process. When the cooperation simulation is run, at each simulation time step, 9 system information in the power system, PV source current, DC bus capacitor voltages, grid voltages, and grid currents are obtained from the simulation and transmitted to the control card. Then the inverter software receives the incoming data, runs the control algorithm, and as a result, 12 IGBT gate signals are generated. These gate signals are sent to the power circuit model in the Matlab. So the gate pulses of the IGBTs are updated. With the updated switching information, the simulation runs to a new iteration step. In the next simulation step, a new current and voltage measurements are obtained. These new 9 power system information are sent back to the microcontroller. A system continues to work cyclically in this way. Simulation results will be presented comparatively in the next section. Active powers transferred. In this section, simulation results are given comparatively. Circuit parameters, control methods, controller gains, and environmental conditions are the same in both systems. Tests are carried out in standard test conditions for PV systems. Standard test conditions for PV systems are 25 degrees Celsius ambient temperature and 1000 watt per meter over 2 sun irradiation. In these conditions, the maximum power point of the PV string is approximately 701 volts, 8.36 ampere, and approximately 6 kilowatts. Figure 7, 8, and 9 show the PV source output voltages, currents, and active powers drawn from the PV source respectively. When figures 7, 8, and 9 are examined, it is seen that the simulation and the cooperation simulation results are approximately the same, and maximum power point of the PV source is reached quickly, and also MPP tracking can be achieved continuously. The active powers transferred from the inverter output to the grid are shown in figure 10, and the current transferred to the grid in figure 11. When figure 10 is examined, the steady state powers settle to an approximately similar point. However, the time to reach steady state is shorter in the cooperation. Power efficiency is approximately 97% for both systems. It can be seen from 11 that inverter output currents are coincident. Total harmonic distortion values are well below the THT limit determined for grid connected PV systems for both simulations. It is smaller than 5%. THT values are measured as 2.2% in the simulation and as 2.62% in the cooperation simulation. Finally, the voltages of NPC inverter input capacitors are given in figure 12. In the figure, it can be seen that the capacitor voltages obtained from the simulation are equal to the ones obtained from the cooperation simulation. In this study, Matlab simulation and Matlab prototype inverter control card cooperation simulation of three-phase, three-level, neutral point clamped, single-stage, transformerless grid-connected photovoltaic inverter circuits and control system are realized. Cooperation simulation has been used to test the control algorithm, which is embedded to the STM32 discovery board before proceeding to the implementation stage. With this method, it is tried to minimize the software-based problems that could be experienced in the experimental work, and it is aimed not to damage the high-cost power system elements such as IGBT. Approximately the same results are obtained from the tested Matlab and Matlab prototype inverter control card cooperation simulations. In the near future work of this study, it is decided to implement the experimental system. Thanks for your kind attention. If you have any questions.
Thank you very much for your nice presentation and contribution, Mr. Yagan. Okay, I cannot see any question in QA section. Is there any question from our speaker? Okay, I have two short questions, Mr. Yagan. As you know, there are three main types of multi-level converters, which are cascaded H-bridge, diode clamped, or you say NPC, and flying capacitor MLC. Why did you choose the NPC grid-connected photovoltaic inverter structure? Are you here? I think there is a connection problem. Okay. Okay. We move on the third presentation. The third presenter of the session, Izmir University of Economics, Ibrahim Alishar. The title of the paper is Flexible Reactive Power Capacity of Full Converter Wind Turbines. The authors, Ibrahim Alishar, Erhan Demirok. Mr. Alishar, could you please first introduce yourself briefly, and then please start your presentation and share your presentation, please.
Yeah, okay, thank you. Hello, everyone. My name is Ibrahim Alishar, and I'm currently a PhD student at Izmir University of Economics, Turkey, Department of Electrical and Electronics Engineering. We have prepared this study together with Erhan Demirok from 9 Eylul University, Turkey, and Department of Electrical and Electronics Engineering. Today, I will present our study, Flexible Reactive Power Capacity of Full Converter Wind Turbines. Okay. As you know, wind turbines have a property of supplying reactive power according to the requirements of grid codes. It is one of the common points among all grid codes. When we look at the reactive power sources of wind farms, the initial source is the wind turbine itself. The other sources are capacitor banks, shunt FACTS devices, and STATCOMs. Another topic here we want to mention about is use of parallel converters. First of all, it is a very well-known concept, in fact, for power electronics applications. Reliability, capacity increase, and efficiency may be the reason for using parallel converters in a power conversion system. And there are some challenges in the applications, such as equal power sharing, circulating currents, and application of various control techniques. Let's continue with the description of the problem and the proposed solution. As we know, wind power converters mostly operate below full load, especially we can say especially for onshore wind turbines. We can visualize this property in this figure. An example, viable distribution at 8.5 meter per second wind speed, and the reference power curve are shown on the same graph. We can show here that we are mostly operate in this region, and it is below the rated wind speed, and in other terms, below the rated power. Another thing is limited reactive power capability of wind farms connected to weak grids. And it may be a problem for grid connection, of course. Sometimes more reactive power can be needed. And the proposed solution is to make full converter wind turbines have an enhanced and flexible reactive power capability. I will explain the solution in the next slides. Here we should keep in mind that this solution is effective for wind speeds below rated speed. Okay, this is the proposed solution with modular converters. First of all, this is not employing a new converter. It is just developing a solution by using the available parallel converters. Imagine that we have a parallel conversion states in the full converter application, and we are adding one more property onto this. Solution is using parallel converters with a spatial controller. Here we should emphasize that we have a full converter wind turbine having parallel converters, and we are applying the proposed solution. I want to repeat it once more again. Here, in a classical application, the power is shared among all parallel converters, let's say equally. As you know, for example, we are always dividing, for this case, into three, the instantaneous power, but we will change it with the proposed solution. In the proposal, minimum number of converter pairs are used for active power transfer, and the remaining converter pairs, if exist, can be used for purely reactive power support by changing the position of switches. Simply, it is a role shifting of back-to-back converters between machine-side converter and grid-side converter. Let me explain an example case with 3 parallel converters as shown here. If we have an instantaneous active power below, let's say, 1/3 of the total capacity, the first converter pair will be, I mean, here, this one, we can say, we can call it the first. This will be responsible for the reactive power, for the active power transfer. And the remaining 2 converter pairs will be available for the enhanced reactive power capability. In that mode, the switch positions will be the opposite of the first converter pair, and machine side converters will also contribute to the reactive power support in addition to grid side converters. Here, a seamless transition from machine side role to the grid side role by changing the controller type is possible to be applied. When we talk about the switch positions, let me explain quickly. For example, this is responsible for active power transfer, and of course, the switch S11 is on while the switch S12 is off. The remaining 2 converter pairs will have the opposite switch positions, and the machine side converter will be added to the grid side converter for increasing the reactive power capacity. Okay, as a summary of the proposal, instantaneous active power generation of the wind turbine is the input for the proposed solution. It determines the minimum number of converter pairs to be included in active power transfer. And also we obtain the number of remaining converter pairs, which will be available for the reactive power support. In this solution, those switches can be either mechanical or electrical switches. Okay, in continuous operation, as you know, the reactive power capacity of the wind turbine is limited by some parameters, such as converter voltage, grid voltage, and converter current. In this study, we have used a reference case for those parameters to evaluate the performance of the proposed solution. And in addition to that, we have chosen a reference wind turbine to use its power curve, that is Siemens SWT 3.6 megawatt wind turbine. Here, we can talk about the simulation results. First of all, this example case study has been done with a comparison method between a single converter pair and 3 converter pairs. In all the graphs, the blue line represents the single converter pair case, and the orange line belongs to 3 converter pairs. As seen on the graph, the study has been repeated for different grid voltage conditions. For example, 1 per unit, 0.9 per unit, and 1.05 per unit. And 2 reactive power flow direction, injection and absorption. For example, we can follow the comparison. Let's say in this graph, this is the case for single converter pair. You can follow the reactive power capacity on the graph. And if we use the 3 converter pairs, you can follow the increase, a significant increase of the reactive power capacity. Okay, let's talk about the effect of number of converter pairs on the reactive power capacity increase. As a general comment, we can say that effectiveness of the method increases with the increasing number of converter pairs because the resolution of the power levels increases. And this gives an opportunity to utilize more percentage of the total capacity. However, even if there is more than 1 converter pair, it will increase the total reactive power capacity by applying the proposed method. As a general comment, we can say that 3 parallel converters give a satisfying result for the proposed method. More than 3 does not bring any further improvement in terms of the reactive power capacity. And let's continue with the effect of wind profile on the reactive power capacity increase. The analysis has been done for a grid voltage at 1 per unit and the number of parallel converters as 3. The effectiveness of the method increases with inversely proportional to the average wind speed of the region on which the wind farm is located. Here, to obtain the average reactive power increase, the distribution function of a wind speed with variable distribution was used to get a weighted average of the capacity increase. Here, blue lines represent the average reactive power increase in both directions of the reactive power flow. As shown on the graph, the percentage of capacity increase is higher in the low wind speeds. Moreover, we can say that red line represents the probability of being in the effective region. Effective region here means that we can use the proposed method. I mean the wind speeds that we can use the proposed method, simply. And for this wind speed range, I mean this is an example case between the 5.5 and 8.5. The probability is nearly between 60 and 90%. And as conclusions, as a summary, we can say that a new control method with parallel converters of full converter-based wind turbines to increase the reactive power capacity further has been proposed. And with this method, the total reactive power capacity of the full converter turbines which uses parallel converters can be significantly increased for both directions of reactive power flow. And this may lead to a reduction or removal of reactive power sources installed in wind farms or in the locations close to the applied wind farm. And the effectiveness of the method increases with the number of parallel connected back-to-back converters, and increases as the average wind speed decreases. If we evaluate the other main issues regarding the cost, we can say that we may expect an increase due to the additional switches and filters. I want to remind that we are applying the method to the already available parallel converter configuration. Yeah, regarding to the efficiency, we can say that we may expect not exactly the same, but a similar result with the baseline. As a last conclusion, the proposed method is a promising solution for enhancement of the reactive power capacity of full converter wind turbines. As a practical application for the increased reactive power capacity of the turbines, dynamic reactive power allocation of wind turbines in wind farms can be a typical application in order to reduce overall losses. In addition, we can benefit from this method as an additional harmonic filter where the parallel converters are in action. Yeah, that's all from my side. Thank you for your participation and listening. If you have any question, I'm ready to answer. We can discuss together.
Thank you very much for your interesting presentation and contribution, Mr. Alishar. Is there any question from audience or from speaker? Okay. Mr. Alishar, I have a short questions. You are using 3 parallel back-to-back converters and additional switches and filters. It's okay?
Yeah.
Can you compare your proposed solution with other methods in the literature in terms of you said some information, but you can information about cost efficiency, complexity, or hardware requirements?
Yeah. First of all, as I mentioned before, maybe several times, because it is important to repeat it several times, we are applying the proposed solution to the full converter configuration, already using parallel converters. A wind turbine, let's say, may have a design to include the parallel converter configurations because of the any constraints. We don't know. Maybe increase the power capacity, the installed capacity, or to have a better efficiency, etc. This is the example case. 3 parallel converters, configuration. We have this configuration already, let's say, and we are adding for each one, we are adding 1 additional switch because, of course, we will have those kind of switches in the design, and we are adding 1 more switch here and 1 more filter to make it as a similar case. If we use this machine side converter in parallel to the grid side converter, if you want to use it for enhanced reactive power capacity. And in terms of cost, of course, we may expect a cost increase, but it will not be significant because the most important cost drivers here is, of course, the back-to-back configuration. The back-to-back converters is itself, and we are adding 1 more switch and 1 more filter for each converter pair. And what about complexity? In fact, here it will be not very complex as we think at the beginning. Why? Because instead of sharing the power between each converter pair, we can choose another strategy. For example, we will use first converter pair up to its installed capacity. Let's say in this case, 1/3 of the total capacity. And after that, we will use the second one. I mean, we will take into operation the second converter configuration, and goes on. Here, the control system is easy. We are checking the instantaneous active power generation, and according to that, we are finding the minimum, the essential minimum number of converter pairs to be included in the active power transfer, and the remaining converter pairs will be available for the reactive power support. I mean, for example, we can use these two converter pairs for the proposed method. And in the proposed method, again, it is very easy. As you know, the controller of machine side converter and grid side converter are different in full converter and even for the other DFIG or other wind turbines. But here, if we are using any converter pair for active power transfer purpose, yes, these will have the classical roles: machine side converter, grid side converter, and the controls will be in operation in the classical way. But if we want to use the machine side converter as a grid side converter together with the grid side converter, then we need a transition from this controller to the another one. But we don't need to be hurry for this one, because this is just a contribution to the reactive power. It is not an immediate action. So a seamless transition is possible in the control system. Therefore, it will be, we imagine that the controller is simple and it can be easily implemented in the control system of the converters, I mean the conversion system, because it is not a complex controller. There is not a loss of formula, loss of calculations. It will be a short and easy control system.
Okay, thank you very much, Mr. Alishar, again for his participation and contribution to the conference. Thank you very much.
Thank you for your question and for your good comment, Mr. Yilmaz.
Okay. As you know, our second speaker had a connection problem. We can give him more time to answer questions. The question is from Mr. Baydan. For cooperation with Matlab and STM32, UART is enough. Do you have any problem while running the test? Please answer, Mr. Yagan.
It is enough as function block, UART protocol and USB to TTL converter are enough. There is no problem.
Okay, thank you, Mr. Yan, your contribution to the conference.
Thank you.
We move the fourth and last speaker of the session, Sinan Baydan from Istanbul Okan University. The title of the paper, A Study on the State of Health of Lithium-ion Batteries. The authors Sinan Baydan, Mr. Murat Ceylan, and Professor Nejat Tuncay. Mr. Baydan, could you please first introduce yourself briefly and then share and start your presentation, please?
Hello, thank you firstly. Good afternoon, everyone. My name is Sinan Baydan. First of all, I would like to thank everyone who contributed to the ELECO organization. I am a master's student of Okan University, and my department is Power Electronic and Clean Energy Systems. My study is about the state of health estimation of lithium-ion batteries. This is the content of my study. Firstly, I'm going to start with an introduction of lithium-ion batteries. Then I will continue with the state of health, aging mechanism, estimation methods, and experiment and results. Lithium-ion batteries are the most advanced chemical energy storage method of today's technology, and the commercial use of lithium-ion batteries is started in 1991 with Sony's handheld cameras. Today, the usage of lithium-ion batteries is increasing day by day, thanks to the competitive features of lithium batteries. They are unrivaled in many areas, such as high energy density, long life cycle, high power density, and so on. There are many types of lithium batteries with many different chemical components. So it provides that lithium batteries are the optimal chemical energy storage method for the most application. As an example, NMC is the best choice for high energy density requirements, and LTO is the best choice for the high power density requirement. As a simple, if we consider the battery as a fuel tank, the state of health is the size of fuel tank, and the state of charge is the level of fuel in the tank. State of health estimation is important because when the state of health estimation error is high, the state of charge estimation error is also high. Because the estimation of state of charge algorithm is dependent on the state of health value. Basically, we can show the state of health and state of charge with these formulas. The aging mechanism can be explained as calendar aging and cycle aging. Both of them are degradation in capacity of different usage forms. Calendar aging is degradation in storage state, and the degradation ratio is dependent on the elapsed time. Cycle aging is degradation in the usage state, and the degradation ratio is dependent on the user profile. User profile of cycle aging can be explained as harsh cycle and rated cycle. Harsh cycle means the high charge or discharge C rates and high temperature or very low temperature conditions. Rated cycle means the nominal charge or discharge rates and nominal temperature conditions. As you can see in the graph, when the C rate increased, the aging rate also increased. Firstly, our purpose was to find an online estimation method that is fast, effective, easy to implement, and has a low processing load. Of course, there are hundreds of...
Thank you.
Of course, there are hundreds of studies about the state of health estimation methods, and each method has advantages and also disadvantages. Model-based methods needs lots of experimental data for efficient estimation, and also models are so complex. and processing load and hardware requirements also is high, and it increases the cost of the battery management system. The experimental methods needs less experimental data and are easy to implement, but direct measurement methods performances depend on the sensor sensitivity. And it is open to environmental noise factors. These methods are not sufficient when used alone, but they are widely used with other methods. Sorry. Indirect analysis methods can be implemented with less effort, and the requirement of hardware is low because of the processing load is low. They are fast and efficient, but for CCCV charging method, the biggest disadvantage of the method is that the battery has to be fully charged from 0 state of charge to 100. Also, the battery temperature affects the results significantly, so the estimation error rate can be increased. So it is not an efficient solution for online applications. The incremental TC, incremental capacity versus delta voltage method is my study. If the incremental capacity analysis is examined with the conventional V versus Q graph, without a fully charged, it is hardly possible to make an estimation. But the modern delta Q and delta voltage graph creates peaks and valley points, 4 valley points. And these points have relationship between the state of health and values, and so it is possible to make an estimation with the with these points in partial charging. I mean, the requirement of the full charge is eliminated. Firstly, I select 7 cells which have the closest internal resistance to each other, and I used Berke precision's battery setup to H cells, and we create 2 groups of cells with different cycle age cells. As you can see, for example, 300-1-1 and 300-1-0. First group used as reference values, and the second group used as making estimations. The aging test conditions are given in here. The user interface of Berke precisions collect the experimental data in CSV format, and I processed the data on Matlab and obtained the required graphs by Matlab. You can see the aging of cells cycle by cycle in here. After the aging test was completed, 2 different capacity estimation tests were applied by us. One of them is internal resistance test with a resistance meter, and the other is capacity test. Of course, the capacity test is more trustable. So the capacity test results are used for the reference. By examining the graph on the left, the relationship between the peaks and state of health can be noticed. When we take a closer look at these points, the relationship is seen more clearly, and it is almost linear. Equations of these points were extracted by curve fitting method and used as a reference equations for state of health estimations. The estimation results are given in here, and the errors in here. The minimum error rate is 0.11 and the maximum error rate is 3.75%. Although the nominal charge C rate of the Panasonic NCR 18650 is 0.5 C. We applied 0.7 C charge rate and 1 C charge rate to get the incremental capacity over delta voltage graphs. And it's shown that you can make an estimation from the A and B points is possible. Of course, when the charge C rate is low, the accuracy of the estimation is higher, but low charge C rates are not suitable for online estimation. At the end of the experiments, in literature, incremental capacity over delta voltage method have two main disadvantages. One of them is requirement to be fully charged, and the other is requirement of low C charge rate. And the result of experiments, we show that it is possible to make state of health estimation in partial charging and high C rates. Also, we show that the ICDV method is an efficient way to estimate the state of health. For future work, we plan to use this algorithm in a real embedded system on a battery pack. Thank you for listening and attention. If you have any question, I can answer.
Mr. Vardar, thank you very much. Your nice presentation and contribution. I don't see any question in the QA section and chat section. Is there any question from our speakers? Oh, okay. Okay, Mr. Vardar, I have a small two questions. First one is, can you comment on how battery chemistry affects your results?
Sorry?
Battery chemistry, you are using lithium-ion. If you use
NMC. It was NMC.
If change battery chemistry, how affects your results?
Thank you for the good question. Actually, the answer is in here. The incremental capacity and delta voltage graph can be changed a little. The peaks peak points, the peak point values can be changed, but of course you need to use a characterization test before the use the algorithm on a BMS. So the curve fitting algorithms can be changed because the ratios and the curves can be changed. So you need to recalculate the equations with the another points.
Okay, the second question is your RMS E is less than 1.5%,
Yes.
and the maximum estimation error is 3.75%. Is okay?
Yeah.
Okay. Have you compared these results with the literature? What range these values?
It is almost about 3 percentage. Somebody's get better results, but in lower C rates.
Okay, thank you very much again for your participation and contribution to the conference. Thank you very much.
It's my honor.
Okay, okay, we are at the end of the session. On behalf of the organizing committee, I would like to thank the audience speakers and the contributors in the 25th session of the ELECO conference. Before closing the session, special thanks to the chairman, Professor Kalanderli, and the committees. Thank you very much. I wish you a great conference and a good weekend. Thank you very much.
Thank you.
Thank you.
Thank you.